Simple harmonic motion. Simple harmonic motion occurs when the restoring force is proportional to the displacement from equilibrium. The restoring force is the force directed towards the stable equilibrium point. We have two equilibrium points, stable equilibrium point and unstable equilibrium point. In stable equilibrium point, if we give a force to this body, it will oscillate inside it. Characteristics of SHM. Repetitive motion through a central equilibrium point, symmetry of maximum displacement, period of each cycle is constant, force causing the motion is directed toward the equilibrium point, that is why the minus sign. F directly proportional to the displacement from equilibrium, and acceleration is equal to minus omega square into displacement. Mass and spring system is simple harmonic oscillator. One side of the spring is fixed in a block and other side is with a mass m. The entire system is on a frictionless surface. The dotted line is the equilibrium position and x is the extension. When we extend the mass and release, it will oscillate about the equilibrium point. Then the restoring force F is given by minus k into x. If we have two masses with two springs and each having an extension of 5 cm and 10 cm respectively, then we can see even though the amplitude is different but its frequency or time period is same. That means two objects having different amplitude can have same frequency or period. The period of oscillation is t is equal to 2 pi by omega, where omega is the angular frequency of oscillation. If k is the spring constant and m is mass of the block, then omega is square root of k by m. We have the same spring and mass system. Here x is equal to 0 is the equilibrium point and x is equal to a and x is equal to minus capital A are the extreme points. At the equilibrium point, the system have maximum velocity, that is Vmax, and at the two extreme points, its velocity V is equal to 0. Thus, at the equilibrium point, the energy is completely kinetic and thus K max is equal to half mv max square. At the extreme points, the energy is fully potential. Therefore, E is equal to U max is equal to half K A square. In between these points, it's a mix of kinetic and potential energy. Thus, the velocity at the end points will be 0 and it is a maximum at the equilibrium point. Now we can represent simple harmonic motion. This is a spring and mass system. X is equal to 0 is the equilibrium point. I am pulling the mass in the direction Fa, that is the applied force. At the same time, there is a spring force Fs in the opposite side. This is at t is equal to 0. So in the graph, this point, the x is equal to A amplitude. And when I release, it reaches x is equal to 0. At that time, spring force is 0. That means it reaches this point, t is equal to t by 4. It again moves to x is equal to minus a. At that time, this is the direction of spring force Fs and it reaches minus a position. That is time is equal to t by 2. And again it reaches x is equal to 0. At that time Fs is again 0. But time is 3t by 4. Then it reaches x is equal to a with a time capital T. So from this point to this point, it complete one oscillation. The time taken for one oscillation is called time period T. And its velocity and accelerations are given when displacement is maximum, velocity is 0 and acceleration is minus omega square times a and so forth. This is the one cycle. The time taken for one cycle is called period. The instantaneous displacement is represented by x is equal to a cos omega t and time taken for one complete oscillation is the period capital T. The velocity is the first derivative of displacement. Therefore, Vx is equal to minus Vm sin omega t, where Vm is the maximum velocity is given by omega a. And acceleration is the second derivative of displacement. Therefore, Ax is equal to minus Am cos omega t, where Am is omega square a maximum value. Now, if the mass spring system is oriented vertically, it will exhibit simple harmonic motion with the same period and frequency as a horizontally placed one. We can represent simple harmonic motion mathematically by x of t is equal to a cos omega t, and velocity v of t is first derivative of x of t, that is minus a omega sin omega t, and a of acceleration is minus a omega square cos omega t, where a is amplitude of motion, that is the maximum displacement from equilibrium, a omega is maximum velocity, a omega square is maximum acceleration. This is not the unique solution. We can represent x of t by a sin omega t, so that v of t is a omega cos omega t, a of t is minus a omega square sin omega t. Differential equation for simple harmonic motion. We have x of t is equal to a cos omega t plus phi, where phi is a phase constant, omega t plus phi is the phase. Therefore, dx by dt is minus a omega sin omega t plus phi, d square x by dt square is minus a omega square cos omega t plus phi, but a cos omega t plus phi is x of t, therefore d square x by dt square is minus omega square x. D square x by dt square plus omega square x is equal to 0. This is known as the differential equation of simple harmonic motion, where omega is square root of k by m and t is 2 pi by omega. Now let us do one example. Here the period of oscillation of an object in an ideal mass spring system is given by 0.5 second and its amplitude is 5 centimeter. We have to find the speed at equilibrium point. We know at equilibrium x is equal to 0 and E is equal to kinetic energy plus potential energy is equal to half mv square plus half kx square, that is equal to half mv square, since x is equal to 0. Since E is constant at equilibrium, the kinetic energy must be the maximum. The total energy is kinetic. Therefore, V is equal to Vmax is equal to A omega. A is given by 5 centimeter. Omega is 2 pi by t, that is equal to 2 into 3.14 by 0.5 second, that is equal to 12.6 radian per second. And we can find velocity as a omega, that is given by 62.8 centimeter per second. That is the maximum velocity at equilibrium point. In this example, we have a diaphragm of a speaker has a mass 50 gram and responds to a signal of 2 kilohertz by moving back and forth with an amplitude of 1.8 into 10 raised to minus 4 meter at that frequency. We have to find what is the maximum force acting on the diaphragm and what is the mechanical energy of the diaphragm. Here F maximum, that is the maximum force, is equal to m into maximum acceleration, that is m into a omega square. M a into omega is 2 pi f all square, that is 4 pi square MAF square. Substituting the values, we have 1400 Newton. Mechanical energy is conserved, that is E is equal to kinetic energy maximum, that is equal to potential energy maximum. Umax is given by half k a square, but we don't know the value of k. Therefore, kinetic energy maximum is equal to half mv maximum square, that is half m into Vmax is a omega square. Substituting the value, we get kinetic energy maximum is 0.13 joule. In this example, we have the displacement, instantaneous displacement is given by y of t is equal to 8 centimeter into sine 1.57 radians per second into t. We have to find the frequency of oscillation. Comparing this with y of t is equal to a sin omega t, a is equal to 8 centimeter, omega is 1.57 radians per second. Frequency f is omega by 2 pi, that is 0.25 hertz, and period t is equal to 2 pi by omega, that is 4 seconds. X max, that is the amplitude, 8 centimeter. Maximum velocity is a omega, that is 12.6 centimeter per second, and maximum acceleration is a omega square, that is 19.7 centimeter per second square. Simple pendulum is constructed by attaching a mass to a thin rod or a light string. This is a string of length L which is considered to be inextensible, and a bob attached with the wire. The weight is mg downwards. The tension is acting on the wire in this direction. Tension is given by T. The components of tension in the y direction is T cos theta, and in the x direction is T sin theta, where theta is the angle. The x equation is force is equal to T sin theta. It is in the negative direction, therefore it is minus T sin theta. This is the origin. This is the negative x direction. Therefore minus t sin theta. And y equation is md square y by dt square is t cos theta minus mg. But there is no motion along the y direction. Therefore 0 is equal to t cos theta minus mg. If theta is very much less than 1 radian, then cos theta is approximately equal to 1. That implies tension is equal to m into g from this equation. Therefore m d square x by dt square is minus mg sin theta. But sin theta, if this distance is x, then sin theta is x by this length L. Let us consider this as a triangle. Therefore sin theta is x by L. M d square x by dt square is equal to minus mg into x by L. That gives d square x by dt square plus g by L into x equal to 0. This is exactly similar to our differential equation of simple harmonic oscillator with omega is square root of g by L. T is 2 pi by omega is equal to 2 pi root L by g. That means the time period of oscillation of a simple pendulum is 2 pi root L by g. The differential equation for oscillation is d square x by dt square plus g by L x is equal to 0. Here a clock has a pendulum that performs one full swing every 1 second. The object at the end of the string weighs 10 Newton. What is the length of the pendulum? We have t is equal to 2 pi root L by g. From that L is equal to g t square by 4 pi square. That's equal to 0.25 meter. Damped oscillations. Suppose we have immersed the mass in a bottle of water. Its oscillations goes on decreases. When there is a dissipative force such as friction, then the amplitude of oscillation will decrease with the time. That kind of oscillations are called damped oscillations. In damped oscillation, we have to consider damping forces. Therefore, F is equal to spring force plus damping force. That is m d square x by dt square is equal to spring force is minus kx. We can assume the damping force is minus b into dx by dt. Dx by dt is velocity. D square x by dt square can be represented as x double dot. X double dot plus b by m. X dot is dx by dt plus k by m x is equal to 0. X double dot plus gamma x dot plus omega 0 square x equal to 0, where gamma is b by m and omega 0 square is k by m. The omega 0 is sometimes known as natural frequency. We assume a solution for this equation x of t is equal to c e raised to alpha t. Substituting the value in equation 4, we have x double dot is alpha square c e raised to alpha t plus gamma x dot is alpha c e raised to alpha t plus omega 0 square c e raised to alpha t. Cancelling c e raised to alpha t, alpha square plus gamma alpha plus omega 0 square is equal to 0. From that alpha is equal to minus gamma plus or minus square root of gamma square minus 4 omega 0 square by 2. That is equal to minus gamma by 2 plus or minus square root of gamma by 2 all square minus omega 0 square. If gamma by 2 all square is less than omega 0 square, we call it as underdamping. In underdamping, square root of gamma by 2 minus omega 0 square is imaginary. Therefore alpha is equal to minus gamma by 2 plus or minus I square root of omega 0 square minus gamma by 2 all square. That is equal to minus gamma by 2 plus or minus I omega 1, where omega 1 is square root of omega 0 square minus gamma by 2 whole square. Therefore x of t is equal to c1 e raised to minus gamma by 2 plus I omega 1 into t plus c2 e raised to minus gamma by 2 minus I omega 1 into t. Since x of t is real, c1 and c2 must be like c2 is equal to c1 star. Therefore x of t is equal to c e raised to minus gamma t by 2 into e raised to I omega 1 t plus 5 plus e raised to minus I omega 1 t plus 5. Or x of t is equal to a prime e raised to minus gamma t by 2 cos omega 1 t plus 5, where e raised to I theta plus e raised to minus I theta is 2 cos theta, that is cos omega 1 t plus 5. A prime is equivalent to 2 times c. Thus in the case of underdamping, displacement is given by a into e raised to minus gamma t by 2 into cos omega t. It is an oscillatory motion with amplitude goes on decreasing exponentially with a factor e raised to minus gamma t by 2. In overdamping, gamma by 2 all square is greater than omega 0 square. In that case, square root of gamma by 2 all square minus omega 0 square is real. Therefore, x of t is C1 e raised to minus alpha plus t plus C2 e raised to minus alpha minus t, where alpha plus or minus is gamma by 2 plus or minus square root of gamma by 2 whole square minus omega 0 square. This is not an oscillatory solution. Both terms are exponentially decreasing. In critical damping, gamma by 2 whole square is equal to omega 0 square. In that case, alpha is equal to minus gamma by 2. But the differential equation would have two solutions. Therefore, x of t is given by C1 plus C2 into t e raised to minus gamma by 2 into t. X of t is equal to C1 plus C2 into t into e raised to gamma by 2 is omega 0. Therefore, e raised to minus omega 0 into t. This also not an oscillatory solution. It all decreases exponentially. This shows a damped oscillation. As the value of gamma increases, the oscillation changes to non-oscillatory solutions. If you have a Q has higher value, we have very good oscillation with a little damping. As the value of Q decreases, the damping also increases. Quality factor of an oscillator determines the amount of damping. Q is energy stored in the oscillator to energy dissipated per radian, that is given by omega 1 by gamma, that's equal to omega 0 by gamma. That means a lightly damped oscillator has Q very much greater than 1, and a heavily damped system loses its energy rapidly and its Q is low. A force can be applied periodically to a damped oscillator. Here we are giving an external force to the spring so that it oscillates with a higher amplitude. We are giving an external oscillatory force so that the spring continues with its oscillation. In forced oscillation, we have spring force, damping force, plus an additional driving force, that is the external force. Therefore, m d square x by dt square is equal to minus kx minus b dx by dt plus the driving force is given by f0 cos omega t. That is x double dot plus gamma x dot plus omega 0 square x is equal to f0 by m cos omega t. Assuming x of t is equal to a cos omega t plus phi is the solution, where omega is the driving frequency. And substituting x double dot and x dot in this equation, we have minus omega square a cos omega t plus phi minus gamma omega a sin omega t plus phi plus omega 0 square a cos omega t plus phi is equal to f0 by m cos omega t. This equation is true for every time, so that if omega t plus phi is equal to 0, then this equation become minus omega square plus omega 0 square into a is equal to f0 by m cos phi, and omega t plus phi is equal to pi by 2. This equation becomes minus gamma omega a plus f0 by m sin phi. Squaring and adding a is equal to f0 by m 1 by square root of omega 0 square minus omega square whole square plus gamma omega whole square as the amplitudes, and dividing tan phi, that is the phase, equal to gamma omega by omega square minus omega 0 square. The complete solution, for example, in the case of underdamped driven oscillator, x of t is equal to a cos omega t plus phi, where omega is the driving force, a and phi are given by equation 11, plus a prime e raised to minus gamma t by 2 cos omega 1 t plus phi. If omega is very much less than omega 0, we call it is slow driving. In that case, from equation 11, phi is approximately equal to 0 and a is approximately equal to f0 by m into 1 by omega 0 square, that is equal to f0 by m into omega 0 square is k by m, that is f0 by m into m by k, that is equal to f0 by k. That is x of t is equal to a cos omega t plus phi, that's equal to f0 by m cos omega t. The driving force balances spring force. If omega is very much greater than omega 0, fast driving, in that case phi is minus pi and a is f0 by m omega square. Therefore, x of t is a cos omega t plus phi is equal to f0 by m omega square cos omega t minus phi. Cos omega t minus phi is minus cos omega t. Therefore, x of t is equal to minus f0 by m omega square cos omega t. If omega is greater than omega 0, a is negative, and omega is less than omega 0, a is positive. A is negative means if the force varies as cos omega t, the displacement varies as minus cos omega t. In the case of omega is equal to omega 0, that is the driving frequency is equal to the natural frequency, then we call resonance. Here the amplitude become more flattened with the damping. Phi is approximately equal to minus pi by 2 and A is equal to f0 by gamma m omega 0. Therefore, x of t is equal to a cos omega t plus phi, that's equal to f0 by gamma m omega 0 cos omega t minus pi by 2. Cos omega t minus pi by 2 is sin omega t. Therefore, x of t is equal to f0 by gamma m omega 0 sin omega t. The maximum value of a is obtained by minimizing denominator of equation 11, that is d by d omega of the factors inside square root is omega 0 square minus omega square whole square plus gamma omega whole square, that's equal to 0. This is a minimization condition, that is 2 times omega 0 square minus omega square into minus 2 omega plus 2 times gamma square omega is equal to 0. From that, omega is equal to square root of omega 0 square minus gamma square by 2. This frequency is known as omega r or resonance frequency. At resonance, the maximum value of A is f0 by gamma m into square root of omega 0 square minus gamma by 2 whole square, obtained by substituting the value of omega r in equation 11.